Hello, everyone. My name is Alex Baker, and I'd like to welcome all of our new and existing users to the Moldex3D standard training. Just a couple of admin things before we get started. Please keep your microphones muted throughout the session to keep the distractions to a minimum. This session is being recorded, and the recording will be uploaded to our YouTube channel, Moldex3D North America. You'll receive a link to watch that video at your convenience later this week. Any questions you may have throughout the session can be sent through the chat section of Teams, and we'll help to answer those questions live. This session is meant to be interactive, and to follow along, you'll need three things: Moldex3D CAD Doctor and Moldex3D Studio 2023 are the two applications we'll be using, and you will want access to those on your desktop. Please also have the consumer folder downloaded and extracted. It contains the model and pre-run simulation file we'll be using throughout the session. If you have not installed Moldex3D, then feel free to follow along visually, and you can review the recording at your convenience. This session is going to be split into three sections. We have the CAD Doctor and importing a model into Moldex3D, which will bring us all the way up into the meshing portion. The second hour is going to be meshing theory and setting up simulation. And then we're going to wrap things up with post-processing after the simulation has been run. How do we interpret the results and get a meaningful output from the simulation? Without any further ado, we'll jump straight into Moldex3D CAD Doctor. I am using the 2023 version for this session, but if you do have an older version, the procedure will remain the same. When you open up Moldex3D CAD Doctor, you'll see that there's an interface over here on the left side. That's where all of our main functions are going to be located. And the nice thing about CAD Doctor is it's very straightforward and simple to use. We're actually only going to be clicking 5 buttons to interact and fix our model coming from our CAD system. Moldex3D CAD Doctor fundamentally is used to convert your model from your CAD system, whatever your CAD system exports, to whatever Moldex3D expects as a quality import. The translation between your CAD system and Moldex3D can create tolerancing differences. Maybe the output tolerance for service connection and the import tolerance for service connection between your CAD system and Moldex3D are slightly different. And that might cause the surfaces to be dissociated or separated from one another. And CAD Doctor really helps us to shore up some of those issues. Also, from a surfacing standpoint, if there's two surfaces that are very close to one another but not exactly contacting, that might cause a problem in the meshing, and CAD Doctor helps to kind of simplify those interactions a little bit as well. The first button that we're going to be clicking on is Import. The Import button will look like a page with a blue arrow. And you can route to the consumer folder. Under the consumer folder in the CAD data folder, I've conveniently put the step file that we're going to be using for this session. Although step files are quite common, we do have the ability to import other file types as well. We have cat parts, we have assembly files from Creo, we have IGES, JT, PRT files, and even Parasolid files. So there's a lot of native CAD files that we can import in addition to step files, although step files are the most universal CAD file type. We'll go ahead and import the step file. All right, a couple of quick mouse controls. You only need to know two things. Rotation is right-click drag by default. You can change that up in your file system preferences. If you want to change to a different mouse control system, you can do so. And then zooming in and zooming out is going to be your middle mouse scroll. That's all you really need to just be able to inspect where certain errors occur on your geometry. All right, so the first of 5 steps is completed. We've imported our geometry. The next 3 buttons that we're going to be clicking in succession from left to right are down here in the main section, right above the navigation panel. The first of those buttons looks like a cube with a magnifying glass, and it's called the check function. The check function will run a 16-step checking procedure that will attempt to identify any sort of issues that CAD identifies or that Moldex3D identifies as a problem for meshing. These issues are going to be split into a categorization that we call severity. There are 3 levels of severity. The top level of severity is called critical. Critical errors we really do want to get rid of before going into Moldex3D. Serious errors we want to try to get rid of as much as possible. We won't spend a whole lot of time getting rid of serious errors. If they're very easy to get rid of, then awesome. If not, then we won't worry about them. And then minor errors are more of like a visual indication. They're not something that I would ever spend any time to go in and fix. If you highlight any of these errors, you'll see that a series of repair tools show up down here at the bottom in the navigation panel, and those allow you to interact with those errors manually if you wanted to. Although our automatic procedure, you'll find more times than not, will remove all of the necessary or most of the necessary problems on your geometry. Next to the check function, we have the auto stitch function, which currently is grayed out. The auto stitch function is associated with the loops of free edges error. A loop of free edges will happen under 2 scenarios. Either 2 surfaces are disconnected or dissociated from one another, as I mentioned earlier. This means that there's a gap between the 2 surfaces. More than likely, that happens because of a tolerancing difference between your CAD system and Moldex. And if you have one of those, usually it's not an isolated instance. Most of the time, most of your services or all of your services will become dissociated. The other scenario is if your service is completely missing, in which case you would just need to fill in the hole using CAD Doctor's fill hole function. In the first scenario, though, the auto stitch tool really allows us to merge those surfaces back together within a new respecified tolerance. Right, so you could use the auto stitch for that. But if the loop of free edges is 0, like what we see here, that button will be grayed out and we can skip over it. If you do have loop of free edges errors, I would highly recommend you to try using the auto stitch tool before moving on to the next function, which is auto heal. Auto heal is going to attempt to fix everything except for the loop of free edges error. So let's go ahead and hit auto heal, and we'll let the function or the kernel do its thing. And then it's automatically going to update this list by effectively pressing the check function once again. Now, something very important to note is that the auto heal function will not touch the contours of your geometry. What that means is if I have a surface that needs to be deleted and reconstructed in order to fix a particular error, CAD Doctor will not do that automatically and will force you to do it manually. The reason for this is because we don't want CAD Doctor to be going in and changing our geometry in a significant way without our knowing. We want the output from CAD Doctor to be as similar to the input. And if there are any differences, we absolutely want to know about them. We don't want to spend all this time to mesh our model, run the simulation, interpret the results, just to find out that some of the features got cleared off of our geometry. All right, so CAD Doctor, the output from CAD Doctor will be as close to the input as possible, maybe with just some minor differences in like the service connection. Maybe if there's like small surfaces that are interacting with one another, if surfaces are very minorly disconnected from one another, that's where the auto stitch tool comes in. But otherwise, the geometry is very similar to the model that we brought in, just a little bit more friendly from a meshing perspective. All right, so just to review that procedure, we did import, check, auto stitch, auto heal, and then the 5th and final button that we're going to be clicking here is export. So it looks like a page with a red arrow right next to the import button. You can export your file into that consumer folder. And the CAD data folder under the consumer folder is kind of an organizational folder that you can use, so you can save it there, or if you want to save it to your desktop, Just make sure you know where you are saving this to. Something of note is the file extension. We are using an MDX-SF extension for our export here. That's a Moldex3D solid file type that can only be imported into Moldex3D applications. However, once you get into Moldex3D Studio that we're going to be looking at in just a moment, you do have the option to export from Moldex3D Studio as a step file. So you can use, as long as you have access to Studio, you can use CAD Doctor to simply fix your geometry and export the step file for other applications as well. All right, I'm going to go ahead and hit save. All right, and that should create that MDXSF file. All right, and now that we have the file that we wanted out of CAD Doctor, we can go ahead and just close out of CAD Doctor using the red X over the top right corner. When you go to close out of CAD Doctor, it is going to give you a slightly confusing message asking you if you want to save the changes. And it might actually seem like you're saving the changes to the step file directly, but actually what this is doing is saving an application file for CAD Doctor. So for example, if I want to come in and fix these minor errors that were left over that usually we don't have to look at, if they do end up causing us meshing problems for whatever reason, we can come back using this file and fix those rather than having to go through that whole procedure all over again. I usually don't save this file, but you can if you'd like. If you expect it, especially if you have a lot of errors that are left over. Most of the time, I'm just going to use those 5 buttons and just send it over into Moldex3D Studio, just because any effort that I spend in CAD Doctor is never guaranteed to yield any sort of time savings in Studio. So I usually like to just do the general procedure, bring it into Studio, try to mesh it. If there's a significant number of errors in the meshing, then I'll bring it back into CAD Doctor and try to maybe fix some of those serious and minor errors potentially. All right, that being said, let's go ahead and open up the Moldex3D Studio application. When you open up Moldex3D Studio, you're going to be faced with 2 options. You can either create a new project or open an existing project. When I say the term project, this is really just a place for all of your simulation runs to be stored. So you can have 5, 10, 50 runs within one project. And when you move to a new geometry or a new set of iterations, you can create a new project to kind of keep things separated. But if I'm running an iterative study, I can keep all of that information within one project, and I can open those up to compare all of the runs to one another. All right, so we're going to use new here to create a new project file. The default is going to be MDX project followed by the date. But I'm going to change this to be something a little bit more meaningful, as having a lot of those projects running around can get very confusing very quickly. All right, so I'll just call this standard training. And the location, the default location will just be your working folder. You can create a subnetwork of folders like you saw I had the support folder. But the working folder is what you created by default when you installed Moldex3D, and you can save it there. Or if you hit the folder here, you can really save it anywhere that you want on your machine. I would highly recommend you to keep the files on your local drive, whether that's the standard C drive or a secondary D drive. If you put your files on an external hard drive or a thumb drive or a network drive or a shared drive, whatever, you have to keep in mind that wherever the files are stored, there has to be a communication with your local drive where the solvers are located. That communication can be delayed if there's a network connection or any sort of external connection. That communication can be delayed, and it, at the best case scenario, will cause your simulations to bog down and your computation time will be longer than necessary. In the worst case scenario, and especially in the case of a network drive, that connection can be broken, in which case the connection to the solvers is broken and the simulation terminates and you waste a bunch of time. All right, so I highly recommend, even if you don't use the working folder, I recommend you to put the simulations on your local drive somewhere, just to keep them, one, all in the same place, but two, to make sure that your simulation time is as efficient as possible. You can press OK, and that will create your project file. And you can actually see over here in what we call the project tree, you can see the first run has been created for us automatically. We can change the name of this run by either right-click. You can see a bunch of options here. You can go right-click, edit remark, or as a shortcut, you can double-click on the run header, and you can just change whatever you want that run to be. Maybe I'll call this the baseline run, just as an example. You don't have to rename your runs, but it does help with making things organized and prevents you from going into every run to see which run is which. Along the top here is what we call the ribbon. This is going to be the procedure that we use for Moldex3D. And we're just going to be following this from left to right. And the nice thing is that Moldex3D kind of routes this around the interface automatically. So quite literally, if you don't know what the next step should be, or if you're lost, just go to the left button that you clicked on, move to the right of that, and that'll just be the next function that you need to implement. All right, so starting off all the way over here on the left, under the new run dropdown, we have a bunch of options that allow us to create, copy, and import runs. All right, so new run creates a brand new run from scratch. Luckily, Moldex3D has created our first run for us, so we don't have to use that function. But if we did want to create a brand new run, then we could do so. Copy run is going to be your premier iteration tool. This is what you're going to be using to copy a set of information. You can then make a change, a small change to that information, run the simulation, and then Moldex3D Studio is great at being able to compare the results to one another. So the copy run tool is extremely powerful, and it allows us to create runs and make a valuable comparison apples to apples. Import run allows us to take a run from a different project and import it into this one. So if I've done a study previously on gate location, I can then import that run into this project and start doing a cooling design optimization or a runner layout or scaling up to a multi-cavity system, that sort of thing. DOE Wizard and Create Run Wizards are grayed out because they are going to be based on a baseline run, which we have not yet established. So those are both grayed out. DOE Wizard is enabled by the expert module. So if you don't have the expert module, you won't see this option. But the DOE Wizard, as well as the Create Run Wizard, allow us to create runs very quickly rather than having to press copy run a bunch of times. They allow us to set up a matrix of runs. The only difference between the two is that DOE Wizard will run an optimization at the end based on what information you're looking for. All right, so the DOE Wizard, if you have any queries about that, we'll be more than happy to demo that for you if you're curious about that functionality. Like I mentioned, Moldex3D creates our first run for us, so we don't actually have to do anything with that first button. And we'll move on to the right of that, which is going to be in the Moldex3D solution, allowing us to select what processing method we want to utilize. We have a bunch of different processing methods in Moldex3D. We're going to be using injection molding for this training session. However, you can see all the other advanced modules that we have available to us. Things like powder injection molding, foam injection molding, compression molding, water assisted injection molding. You see all those under here. They just allow us to implement different molding structures and different molding strategies and see the impact on the final part geometry. Again, if you do have any queries about these advanced modules, we can certainly demo those for you at a later time. To the right of that is our meshing type. We have 3 different meshing types: solid, E-design, and shell. 99% of the time, you're going to be using solid. Solid allows us to implement what we call the boundary layer meshing strategy. It allows us to create a true 3D solid mesh. for every component of our mold geometry that we either import or create inside of Moldex3D. eDesign is a little bit more automated. It's not a true 3D mesh. It creates voxel elements that are essentially 3D, but they don't follow the contours of our geometry exactly. And because of that, we have to create kind of an approximated mesh for our mold. So the eDesign strategy, nice for very complex geometries that are difficult to create the solid mesh using our boundary layer meshing strategy. And that's pretty much the other option that you would utilize. The third option here, shell, is for specifically comparing to other shell solvers if you to validate the accuracy or to make a more apples to apples comparison to other 2.5D solvers. We do have that capability as well. But most of the time we are just going to be using the default, which is solid. To the right of that is our import function. For you guys, it should say import geometry. If you just installed Moldex3D, we can go ahead and hit that. And we're going to find the MDXSF file that we just saved from CAD Doctor. All right, so you can find that MDXSF file and import it directly. You can see all of the different import files that you can take into Moldex3D here. Most of these are maybe solid mesh files from stress solvers or from structural solvers. But you do see those CAD Doctor extensions as well. So we're going to import that MDXSF file. All right, we can see that it's brought in as a solid gray geometry. Before we move any further forward, let's go into some mouse controls. Like CAD Doctor, right-click drag is going to be your rotation. You can also use middle mouse click drag as your rotation as well. We do have the ability to do left click drag, but because our left click is typically our selection, you'll need to toggle off this button down here at the bottom right corner of your screen. That is called select. This will disable the ability to select objects and will allow you to rotate using your left click drag instead. If you hold the shift button on your keyboard and right click drag, that will allow you to pan your model. If you hold the control button on your keyboard and right click drag, that will allow you to do more of a controlled zoom. Usually I'll use the middle mouse scroll for zooming, but you can use the control right click drag to do more of a controlled zoom based on your model center. Like I mentioned earlier, there is the left click drag, or I'm sorry, left click, which just selects your model. But we do actually have a pair of box selections utilizing the left click drag functionality. Left click dragging from left to right will select anything that is completely contained within the box that you create. So if I only get a portion of my geometry within this box, it is not selected. Going from right to left across the screen, however, will select anything that the box encounters, even if it's just a small part of the geometry. All right, so just a couple of different selection strategies for you to make things easier when you have a large number of objects in your model. Going back up to the ribbon up here, you can see that because we've imported our geometry, Moldex3D has automatically identified that we need to go over to the model tab. So it has brought us there automatically. And as such, we're going to go all the way back over to the left side. And you can see that the first button is import geometry once again. So if I wanted to import my runner or my cooling system or inserts, even my entire mold assembly, if I wanted to, I could go ahead and do that. In this case, I'm going to be creating everything I need within Moldex3D with the exception of the part itself. So I don't need to import anything and we can move on to the right from there. The next button is check geometry. Check geometry will try to identify any sort of problems that came over from either the CAD system if you imported your step file directly, or anything that was left over from CAD Doctor that we didn't fix. In this case, there is one tiny edge and one sharp face angle. You can turn those on using the radio buttons to the left side of those errors. And if you highlight that particular error, you'll be able to select it because of the for the name tiny edge. You can imagine that this is going to be a very small feature on our geometry, and we can use the little magnifying glass up at the top of this menu to zoom in on it. You might need to rotate around a little bit to actually see where this occurs on the geometry. You need to adjust your rotation angle. We can see that this tiny edge is in fact just a very small feature on our part. And the reason these are identified is because ultimately we're going to be converting our geometry into a series of triangular surface mesh elements. If I have some larger surface mesh elements out here, ultimately that surface mesh size has to decrease to get down to this feature edge length. That can cause a mesh size discrepancy, which can propagate a percentage error in our simulation. We want to avoid that as much as possible. Now, one tiny edge isn't going to be a make or break sort of identification. If I have just a couple of tiny edges, actually the number I use is 20. If we have more than 20 tiny edges, that usually indicates to me that we have a repeated feature or a very intricate feature that needs to be adjusted before we try to go and mesh those. And that can be done through CAD Doctor as well. Sharp face angle, as the name might suggest, is where two faces come together at a very sharp angle. All right, so we can see that this flat face and this filleted face kind of come together and approach kind of a 0-degree angle. The reason this is a problem is because it's difficult to create solid mesh elements in a small volume like that. And in some cases, you'll get a bad orthogonality error or any sort of other solid meshing error where we cannot fill in solid mesh in that small volume. In those cases, we might recommend to either remove the feature or try to open up that angle as much as possible once you get to the surface mesh. Again, these aren't make or break problems because they're not guaranteed to cause any sort of problem in the meshing, but we do recommend you to at least be aware of their presence. You can exit out of the fixed geometry function, and we'll move on to the right of check geometry, which is going to be attribute. Attribute is just a fancy term for telling Moldex3D what this object is supposed to do in the simulation. When we import a model, I'm going to left click on my geometry. When we import a model, it's always going to have this dark gray color. And the default attribution is going to be set to none. We're going to tell Moldex3D what this object is supposed to be by changing the attribution to part, because this is the part that we're trying to mold. You can see all the different attribution types here. Things like part inserts, cold runners, hot runners, and so on. They all have different colors associated with them as well. And you'll get more and more familiar with those as you use Moldex3D. You can close out of the attribution menu. And you can actually see that some of the other buttons have been lit up on the interface. But we're just going to keep going from left to right across the ribbon here. The next button to the right of attribute is model thickness. Model thickness just gives us a very generic representation of the thickness distribution throughout our part. To more avidly describe the thickness, we're going to be adjusting the scale over here on the right side. You can go to the top of your scale and left click drag that downwards until a major region of your part becomes red and starts to disappear. At that point, you could just take the maximum on the scale and say that that's the thickness in that region. In this case, I would say that this wall is about 3 millimeters thick. I can keep going for the next set of features. In this case, it looks like the nominal thickness, which looks to be about 2.5. And we can keep going down for our next feature, which looks to be somewhere around like 2. All right, so this is just a way for you to very quickly identify and get familiar with a geometry that you might not have too much interaction with previously. If you're like me and you don't like this this thickness distribution overlaid, we're going to go back to the model tree and select model, and that will get rid of that distribution. All right, so going back to the model tree right underneath, I'm sorry, the project tree, right underneath the import geometry function, there's a series of tabs. The first of those tabs is going to be our project tree, and that will bring us back to model. The model, you can kind of switch between the colorless model and the thickness color distribution here as well. Moving on to the right of model thickness, we can create a gate for ourselves. Selecting a gate location is quite easy in Moldex3D. I'm just going to use the generic gate function, which is synonymous with the add pin gate if you click on the dropdown. You'll also see all the different types of gating options we have available as well. All right, I am going to use the add pin gate here. And then all you need to do to place a gate on the part is hover over the surface and the location on that surface you want to place the gate, and left click. This will create a gate normal to that surface. Even if it is a curved surface, for example, it'll create the gate normal to that surface. And Moldex3D will identify, based on the size of the geometry, what gate diameter should be used. This gate parameter refers to the bottom diameter of our gate. So the bottom diameter here is 4 millimeters currently. And it depends on what unit system you're in. If you're in inches, then it will be in inches. If you're in millimeters, it'll be in millimeters. You can change the dimensions of this gate later on by reattributing it. Just like we did for the part, you can attribute this object as well. And it will give you control over the top diameter as well as the length of this gate. We can press the green check mark to move on. And this solidifies the gate on our geometry. Now, to keep things simple, I'm going to forgo the inclusion of a runner. You can use the runner wizard to create a runner system for you if you'd like. However, in this case, I'm just going to assume this is a gate location study, in which case all I need is a gate, the melt entrance, which is the top arrow here. If you don't have the melt entrance in your geometry, it looks like a red surface on the top of your gate. I'd recommend to hit the button to the right of runner, which is the melt entrance automated function. And that should place the red arrow as well as the red surface on the top of your gate here. Now, as far as a filling and packing simulation is concerned, if I just want to see how the material is going to flow through my geometry and what is the packing effect based on my gate location, all I need is a part, the gate, and the melt entrance. That's all I need. I don't need anything more than that to run a filling and packing study. However, if you want to run a warpage analysis, if you want to see how this part is actually going to look like after it's been ejected from the mold, you need some sort of cooling system. If you don't include a cooling system, you try to run warpage, we have to assume that there is a uniform temperature condition on the surface of your part, which would be equivalent to the mold temperature that you set in the process. If the surface temperature is completely uniform, There's going to be no differential temperature effect in our warpage calculation, and that's going to create a much lower magnitude of warpage from the simulation than what you would see in reality. All right, so for warpage calculation, it's very important to create a cooling system even if one hasn't been designed yet, and that's what I'm going to do here. We're going to implement what's called a dummy cooling system, which is just a stand-in for a cooling system, just a generic cooling system to imply some sort of realistic heat transfer condition based on our part's geometry, rather than assuming that all of the surfaces are completely uniform in temperature. To start off, I'm going to go into the cooling system section and hit mold base. This is going to create a box around my geometry. There's a few dimensions to worry about here. The first one, and probably the most important one, is the parting direction. This should be identified automatically based on your gate direction. If it is incorrect for whatever reason, you'll want to change it to make sure that the mold open direction is proper. The length and width dimensions down here allow you to control the dimensions of the mold base. And if you hit the blue arrow up here at the top, you'll have access to the height dimension. Now, although you do see the cavity and core height as separate dimensions here, it should be noted that in the simulation, we do not separate the cavity and core sections of the mold. This is just going to be one solid block. And as such, even though we have a red, almost like a red parting plane in the middle of our geometry here, if I rotate down to the side, let's see that that is more around the center of our geometry and not necessarily where the parting plane should be. And that's actually fine because, like I mentioned, we don't actually open up the mold base. And so the location of this parting plane is not really that important. This plane actually is just used for projection when we go to calculate our clamping tonnage. And we just want to make sure that the orientation of our mold is correct. That's the most important thing here. I'm just going to leave the default dimensions of the mold base intact, and you can go ahead and press the green check mark to finish out that function and create the mold base. The mold base by itself is not enough to define a cooling system because although we have places for heat to go, we don't have a place to extract that heat from the mold continually. That's where the cooling channels come into play. To the right of mold base, remember we're just going left to right across the interface here. To the right of mold base, we have the cooling channel wizard. You can go ahead and click the generic function. If you click on the dropdown, you can go to the cooling channel wizard. We do have a couple of other options here as well that you can explore. The cooling channel wizard will just create a bunch of straight cooling channels across our mold from one side to the other. We have the ability to control the direction of those channels. Note that the parallel direction to our mold opening axis is going to be grayed out. So in this case, our mold open direction was the x-axis. So you see that's grayed out, but we do have the ability to apply the y and z axis. D controls the diameter of these cooling channels. You can use a little up and down arrows to see what each of these do. I'm just going to use the default diameter. N is the number of cooling channels on the top and bottom. I usually reduce this just to kind of clean up my element count a little bit. I usually use somewhere between 6 and 8 cooling channels for this dummy cooling system. So you see that this creates 6 cooling channels on the top, 6 on the bottom. All right, and then the last two dimensions, C controls the spacing between these channels. So if I increase this to 60, for example, you can see that spreads out. And we want to increase this until the cooling channels kind of span the width or the length of the part. We want it to cover the entire modeling dimension. The last dimension here, H, is going to be the most important one to pay attention to. If I have my cooling system as it is right now, there's going to be a localized cooling effect that's going to imply some sort of variability to our simulation. And what I mean by that is that this location on my part is going to be much more efficiently cooled than the space between the channels. It means that the temperature right here is going to be lower than the temperature right here. That means that the channels are acting independent of one another to extract heat from the surface of the part. That's going to imply some sort of unrealistic temperature distribution, which is almost as bad as not having a cooling system at all. To eliminate this problem, we're just going to push the cooling channels a little bit further away from the part so that the cooling channels act almost as one unanimous heat sink, that the cooling channels work together to extract the heat from the mold rather as independent lines. The H dimension that I usually set is going to be 10 times the diameter. And usually I'm going to be using the default diameter that Moldex3D gives me. So in this case, I'll be using a height of 80. This will push the cooling channels far enough away from the part that the cooling channels act as one heat sink, but they're still close enough to the part to make sure that we get some sort of efficient heat transfer. Once we're happy with that cooling channel layout, you can press the green check mark. That will solidify the cooling channels, and it'll also place inlets and outlets on the cooling channel ends. The last thing that we're going to be doing in the model tab is the check cooling system. I did skip over the inlet outlet button that does allow us to create the inlets and outlets if we're using a more customized design. But if we use the cooling channel wizards, those inlets and outlets are placed automatically, so we don't have to utilize that function. The check cooling system will check to make sure that everything is working properly. Primarily, it's checking to make sure that one, all of the inlets and outlets have been placed. Two, that the cooling channels are not intersecting any sort of geometry. And three, that the cooling channels are in contact with the edges of the mold base. This is actually a constraint or a requirement in the solver. We need these cooling channels to be attached to the mold base wall in order to run the flow calculation. It also checks for a bunch of other minor things, but those are the three primary components of the check cooling system that are utilized here. All right, we'll take a quick break. We'll take maybe we'll take 10 minutes of a break. And we'll come back and we'll start talking about meshing, how we can convert this newly created model into a series of mesh elements that are capable of running simulation on. We're also going to go through selecting a material and define the differences between CAE mode and machine mode in the process. If you do have any questions, you can send those through the chat function of Teams, and we'll be happy to answer those in this break as well. All right, welcome back, everyone. And in the second section of this training, we're going to be going through meshing theory and setting up simulation all the way up until actually pressing the run button. At the current moment, we have our part, we have a cooling system, and now all we need to do in order to set up the simulation to run is generate the mesh by converting all of these objects into solid mesh geometry. To do so, we're going to go over to the Mesh tab. We have to click on the Mesh tab manually. This is the only place that we have to actually go from tab to tab manually across the top of our interface here. All right, so we'll go over to the Mesh tab. We see that our mesh type has been selected for us already because that's what we specified back in the Home tab. And when we're talking about meshing in the solid mesh specifically, in the solid meshing style, I should say, there's two meshes that are going to be created for every geometry object. There's going to be a surface mesh and there's going to be a solid mesh. A surface mesh is going to be breaking down all of the individual surfaces in our geometry into a series of triangular surface mesh elements. And then we're going to fill in those surface mesh elements through the thickness of our part with a solid mesh. All right, so there's two meshes that we need to specify the parameterization for. For other types of objects, like for example, our cooling channels or our runner, if you highlight your gate, you'll see that there's a center line going through the middle of the gate, which is an indication that this is a line-defined object. Although it looks like a geometry, although this looks like it's a solid object, it is actually just a line that has the volumetric approximation based on the attributions we provided. Because of this line-defined technology, we don't have to create a surface mesh for these objects. They just receive a solid mesh, and I'll explain how that interaction works once we get there in the solid mesh parameters. But for geometry objects like our part here, we will be specifying two types of mesh, or the parameterization for two types of mesh, which will be the surface mesh and the solid mesh. Starting off, just going from the left to the right here, the first button that we encounter that we can interact with is the seeding function. The seeding function is going to allow us to apply the template for the surface mesh to break down our surfaces to a bunch of triangular surface mesh elements. When we press the seeding function, it's going to give us a default mesh size. And to see what that mesh size does, you can hit apply. Apply is going to place a bunch of black nodes on our part geometry, which are going to represent the locations for these triangular surface mesh objects to be started from. You'll see that there's no internal nodes on the surface, and all of the internal nodes that would be created for our triangular surface mesh elements are going to be created randomly. But they're all going to be based on the number of nodes along the feature lines here. If I increase this number, we'll be able to see what that does to our surface mesh, or I should say to our node seeding specifically. So if we go to a mesh size of 10 and hit apply, we see that that spaces the nodes apart, decreases the number of elements overall on our geometry. And if we go to a mesh size of, let's say, 1 and hit apply, we see that that drastically increases the number of nodes on our part and would increase our mesh density across our geometry. Now, this number that we specify here directly represents the nominal distance between the nodes in millimeters. All right, so theoretically, these are about 1 millimeter apart from one another. The reason they might not be exactly 1 millimeter apart from one another is because each feature line has an equidistant constraint where every set of nodes has to be the exact same length from one another, or the exact same distance to one another across this feature line. And as such, we might not get exactly one, but we're going to try to get as close to the specified mesh size as possible while maintaining that constraint. Now, when we adjust the mesh size, we are trading off between two very important simulation components. If I have a low mesh size like this, it means that we have a lot of nodes on our part, which is going to mean that we have a lot of elements. If anybody's ever run simulation before, you'll know that a lot of more elements means more computation time. But on the other side of that, if I look at, for example, this radius here, the more nodes we have, the better approximation we're going to get for certain small features. So for example, if I flip to the bottom of my part, these bosses, for example, with a surface mesh size of 1, we get a pretty good approximation. But if I go up to a surface mesh size of 10, for example, we see that that approximation becomes much more generic. If I look around the circumference of this boss, we see that there's only 1, 2, 3, 4, 5, 6 nodes defining the circumference, which means that when we go to create a bunch of triangular elements, this is going to become hexagonal, and it's not a very good approximation of a circular feature. So when we are specifying our node seating, we're really trading off between the approximation of our geometry with these triangular surface mesh elements and computation time. And to arrive at a meaningful middle ground between those two components, we have a very important strategy for node seating called the Goldilocks method. The Goldilocks method is going to require a pretty specific rotation angle. First things first, I'm going to rotate my part around so that I'm looking down on the top of it. So I'm looking down in the parting direction. Second of all, I'm going to rotate the part so that the longest dimension is horizontal on my screen. And finally, I'm going to zoom in my part so that it fills up the entirety of my modeling window, either from top to bottom or from left to right, whichever one hits first. The reason we do this is because now we have normalized our part to our modeling window. And that means that we can apply the same sort of strategy for any size part that we bring into Moldex3D. It doesn't matter if this part is, 100 times the size of this or 100 times smaller than this. We're going to be applying the same sort of strategy, and the only thing that's going to change is the actual number for mesh size. The reason this works so well is that we are going to be looking at the relative spacing between these nodes. And the way that the Goldilocks method is specified is we want there to be about 2 to 3 nodes width of space in between the individual nodes here. When I say 2 to 3 nodes width of space, it looks something like this. So the dark black nodes are the actual ones that show up. And this is about what we want. So visually speaking, each node has some sort of width to it. We want there to be about 2 to 3 nodes width of space in between the individual nodes. Anything less than that is too fine. Anything greater than that is too coarse. We want it to be right in the middle or in that Goldilocks zone. All right, so if I look at it visually, and this is not really scientific necessarily, it's more of a visual approximation. A mesh size of 10 gives us something like 5 to 6 nodes of space, which is a little bit too much. So maybe I'll have that. Going down to 5, looks like maybe close to maybe just a little bit more than 3, so I'll reduce that a little bit more still. All right, and a mesh size of 4 seems to be right around that 2 to 3 nodes width of space. So I would say that a mesh size of 4 is pretty good for this model. You'll actually note that this is pretty close to what Moldex3D gave as a default. And over the last 5 years or so, we have been improving the kernel and the recognition of this kernel to our geometry to give the best default approximation of a Goldilocks mesh size as possible. And so more times than not, you can just trust the defaults. But I always recommend to come in and check out what Moldex3D is giving you for a mesh size. And especially for simple geometries, the funny thing about this default is that it gets more accurate the more complex the geometry gets. And that's because the more feature lines we have, the better approximation of an average feature line length we have, and therefore we get a more accurate default setting. If I have a box that only has 12 feature lines on it, it's going to be difficult to verify what the average node seating should be. And you, for most of the cases for simple geometry, you get a much larger node seating than you should. All right, so it's always a good idea to come in here and at least verify what Moldex3D is giving you. And especially if you're trying to favor computation time, maybe you can increase that mesh size just a little bit to decrease your computation time marginally. Once you're happy with the global node seating, you can go ahead and press the green check mark. And this will bring you into manual node seating. So what we just did is we set the node seating equivalent across every single feature line on my geometry. But let's say there's some features that need refinement. So like, for example, even though we have a Goldilocks node seating, we still see that there's only 6 nodes around this feature, which in order to get a sufficient number of nodes, we might have to go down to something like 1 for the entire part geometry. But luckily, this manual node seating allows us to go in and select a group of feature lines. You can use that left click drag box select to select all those feature lines on the boss. Then we can either change the number of segments or we can change the mesh size. In this case, the number of segments isn't going to be too useful because the length of the feature lines across this feature or across this boss are not equivalent in length. And so the mesh size is going to be much more appropriate. So we'll change the mesh size, and I'll change to a mesh size of 1 since we saw that the node seating was pretty good for that node seating earlier. You can repeat this for the other 2 bosses as well. I'm going to keep it as is just so I can contrast this when the mesh is actually created. But if you want a little bit of practice for setting this manual node seating, you can do so on the bosses 2 and 3. I won't spend a whole lot of time in this manual node seating just because Moldex3D does a lot of manual or automatic refinement for us in the kernel. So I'll usually just focus on some of the smaller features. If I have a logo, if I have a rib or some small feature, I'll usually go in and node seed those slightly different. But the mesher is pretty good at refining around tight interactions or very obscure interactions just to make sure that the approximation of those features is as good as possible. Kind of like what I mentioned with the tiny edge, like this guy over here. We want to avoid a large amount of surface mesh variance, surface mesh size variance specifically. So I don't want to go in and refine every single small feature on my part. I usually only want to refine the ones that are crucial to the analysis. So for example, if I'm not even too interested in these bosses for the analysis, I might not spend the time or the elements to go in and refine them. All right, once you're happy with the node CD, you can go ahead and press the green check mark, and that will bring you back to our model. And that is the end of the surface mesh parameterization, now we can get into solid mesh parameterization. To do so, we're going to skip over the generate function for the time being, and we're going to go to the parameter function. Parameter allows us to specify what the structure of our boundary layer mesh is going to look like. Before I jump too much into this parameterization, I want to show kind of visually what's going on in the background of our mesher so that everybody has a little bit of understanding as far as why we use a boundary layer mesh. Every region on our geometry is going to have two bounds. It's either going to have a top bound and a bottom bound, front and back, left and right. However you want to consider this, we are looking through the thickness of our part constrained by the upper surface and the lower surface. What we just did in the node seeding is we placed a bunch of nodes to create a template for a surface mesh across the upper bound and lower bound. And what we're going to be doing in the solid mesh is we're extruding these nodes downwards from the top and upwards from the bottom to create a 3-layer structure. The top and bottom layers are called the boundary layer mesh, BLM, and this middle layer is more like a connector layer between the two called the tetra. Typically, this boundary layer section is going to be divided into sublayers. In this case, we have what's called a 5-layer BLM, where we have 5 layers on the top, 5 layers on the bottom. And you can actually change how many layers are created here through the first parameterization option that is called mesh type. I guess second below the attribute. You'll see that the maximum number is 5 layers. If you want to save a little bit on your computation time, you can go as low as 3 layers. But there's other methods to reduce your computation time that don't affect the results directly. And although there isn't a large amount of mesh dependency, the resolution of the results that you get from a 5 layers BLM is quite a bit better than a 3 layers BLM. So I would always recommend to use a 5 layers BLM. Which gives you 11 layers through the thickness. We have 5 layers on the top, 5 layers on the bottom, and then 1 layer through the middle. So 11 layers total. And each of these layers are going to be relatively uniform in thickness, giving us the lowest amount of mesh dependency possible. Now, in an ideal world, I would actually just be able to extrude from one node all the way through the thickness to the node on the opposite side. But unfortunately, because the surface mesh on the bottom side of our part can never be the same as the surface mesh on the top side due to, let's say, there being a logo or a rib or a boss or some other feature. There has to be a difference, or there has to be a separation between the boundary layer on the bottom side and the boundary layer on the top side. This tetra layer allows us to connect the two almost like a layer of glue. And allows us to finish off the solid mesh through the thickness of our part. Now there's 3 different types of elements that we use in Moldex3D, and I'll go through them quickly here. Tetrahedral elements appear in the tetra layer. They are 4-sided triangular elements, and the benefit of these is that they're very flexible. You can pull any one of these corners without really significantly impacting the other 3. And that makes them very good for structural calculations or wherever you need some sort of transition in mesh, like between the 2 boundary layers, for example. And you'll actually see these very commonly in structural solvers because of their ability to have stability in calculating large-scale deformation. All right, so for a boundary layer mesh like this, the second type of element is a little bit more rigid, and it's called the prism element. It has a triangular top and bottom, and then quadrilateral sides. The quadrilateral sides make this much more rigid, and therefore the structural calculation is a little bit less stable. Luckily for Moldex3D, we don't really do structural calculation too much. And they are actually quite beneficial for flow calculation because of their structure in the thickness direction of our part. If you're thinking about a fluid flowing along the thickness direction here, Any location along this mesh, we're just going to be following along a layer pretty much, which makes the calculation not only stable, but it also makes the results a lot better resolution than something like a tetrahedral mesh, which is a little bit more randomly oriented and more randomly distributed. The third type of element that appears in Moldex3D, not necessarily in the boundary layer mesh, but in Moldex3D in general, is the hexahedral element. Hexahedral element is effectively just two prism elements put together and is generated from a quadrilateral service mesh layout. So if I, instead of triangular service mesh elements, if I have quadrilateral elements that I'm extruding, then I get this hexahedral mesh. The quality of these elements is going to be dependent on the number of nodes that each element possesses. So for example, a tetrahedral element has 4 nodes, 1, 2, 3, 4. The calculation itself is going to be done on the nodes. And so the results that you see, if you were to take a slice through the part, the results that you see are an interpolation of the information at these nodes to that location within this element. So the more nodes we have on our part, the more interpolation points we have, and the better precision we get for the for that interpolation through the thickness of our element. All right, so a tetrahedral element has 4 nodes, prism element has 6, and a hexahedral has 8 nodes, meaning that the hexahedral is the highest quality element, followed by prism, followed by tetra. But you might notice something interesting. The tetrahedral elements, although they're the lowest quality, are right in the middle of our mesh, which might raise some red flags in that the tetrahedral elements might have too much of an impact on our results. And we actually thought this originally as well. But if you look into the results a little bit more, for example, if I look at the injection molding velocity profile, we can get an idea of how the impact of the tetrahedral layer is going to be on the results here. If we look at the velocity profile, we see that there's a 0 velocity right on the mold surface, and the maximum velocity occurs right in the tetrahedral layer. You might think, Alex, okay, this just proved my point that the tetrahedral element is calculating the most severe information. But actually, the magnitude of velocity is just a number. It's just a series of binary digits. The value of an element is not necessarily in the magnitude of the result that's output, but rather the change in the result that's output. All right, so the change in velocity across this tetralayer, if I draw an arrow down to where the tetralayer contacts the edge of this profile, the change in velocity over this tetralayer is very, very small with respect to the amount of velocity change that's occurring in the boundary layer section. Each of these layers in the boundary layer mesh are quite large in the amount of gradient, as we call it, or the amount of change in information that's being calculated. And this makes the boundary layer much more important. I shouldn't say important, much more useful in bringing forth the resolution of results that we need to be able to get accuracy from our analysis. Now, the second parameter that shows up in the Moldex3D solid mesh parameters is the boundary layer offset ratio. The boundary layer offset ratio is going to be defined by a governing equation that you can actually see on the interface in the note here. And that's going to break down to T equals S times OR. T is the boundary layer offset distance, or the boundary layer thickness. S is the mesh edge length, or you can think of this like the node seating. And then OR is kind of this scalar parameter that allows us to define the ratio between the boundary layer thickness and the mesh edge length. If I rearrange this equation, we'll be able to see that the offset ratio is quite literally a ratio between the offset distance and the mesh edge length. So if I had a boundary layer offset ratio of 1, That means whatever my node seating is, that's going to be equivalent to my boundary layer offset distance. It means that these two are 1-to-1 with one another. If I have a boundary layer offset ratio of 10, that means that the thickness of my boundary layer is 10 times my node seating. Just as an example. Visually, what that looks like is if I have a low offset ratio, that means that my boundary layer thickness is going to be small. And the gap that's created has to be filled with tetrahedral elements. That means that the tetrahedral elements in their random orientation have more of an impact on the results than the more structured boundary layer elements or prism elements. And that's actually not preferable. We want the boundary layer or the prism elements to dominate through the thickness of our part. And so we actually want a higher offset ratio than that. However, theoretically, if we go too high in the offset ratio, we can get a situation where the two boundary layers overlap one another. If the boundary layer offset distance is greater than half the thickness of the part, we can get a situation where the two overlap one another. And this actually used to be a huge pain for us because we'd have to create the mesh. It would fail because of overlapping. We'd dial back the offset ratio, and it'd be this constant iterative loop to find the ideal boundary layer offset ratio. Luckily, that doesn't happen anymore. We have an algorithm in our mesh kernel that says if there's overlapping mesh that's going to occur, we're going to dial back the offset ratio automatically so that there's a minimum tetra layer through the middle of our thickness, which, as it turns out, is going to be our ideal BLM. All right, so actually, we're going to take advantage of this in the user interface. And we're just going to set the boundary layer offset ratio as high as we possibly can. We're going to set it to the maximum, which if I type in 10, for example, you'll see the constraints of the boundary layer offset ratio show up. The minimum offset ratio is 0.1, and the maximum is 3.0. All right, so I'm just going to set the maximum value of 3.0 as my offset ratio, and that's what I'm going to use for every part in Moldex3D. Now we do have some different recommendations for each of the different attributions in Moldex3D. If you want to take a screenshot of this best practices, you can certainly do so. These are our recommendations for each of the different attributions. If you bring a geometry in for things like runners, inserts, and cooling channels. Keep in mind that this does not apply to line-defined objects. That's going to be coming up next. Moving on to the bottom section is our curve meshing, and this is going to apply to anything that is a line-defined object. All right, there's two possible objects that can be line-defined. We have the runner, which includes gates, and we have the cooling system, which includes both cooling channels and heating rods if you're using a thermoset, or if you have a heating element in your mold, that can also be defined as a line. The way this is going to work is we're going to define a two-dimensional template. That two-dimensional template is going to be pasted onto the entrance of that object. And then it's just going to be extruded along that line to create the solid mesh. Now you'll notice that the template here is purely quadrilateral in nature, which means that when we go to extrude this mesh, it creates hexahedral elements. Which, if you remember, hexahedral elements are the highest quality elements possible in Moldex3D, and actually, as it turns out, in computation in general. And they are perfectly contoured to the geometry that we are trying to specify. So very, very powerful meshing technology that we have for line definition. I would highly recommend everybody to try to approximate their cooling systems and runner systems with lines whenever possible, just so you can get this very powerful or this very high quality and high precision solid mesh. Now, the template that we use here is typically 4 in or 5 outer. You do have the ability to customize this if you want to, but the default is perfectly fine. For cooling channels, same thing is follows true. The only difference in cooling channels, sometimes I do like to increase the outer layer count if I am specifically interested in how the flow looks like through the cooling channels. If I'm interested in the characterization of flow, sometimes I will increase this outer layer count, but generally speaking, I will keep a default. All right, once we're satisfied with the solid mesh parameters, we can press the green check mark. The nice thing is, once we create our mesh, which we can do so by hitting generate, and then we can hit generate one more time. The nice thing is that once we generate our solid mesh and save the mesh file, all of the parameters that we just set in that solid mesh parameter section get saved automatically. All right, so we don't have to go in and set those every time. Those will become the new defaults going forward for your next simulations, even if they are in different projects. Now, the mesh that's created here, we get our surface mesh, which again looks like a bunch of triangular surface mesh elements. We go to the bottom here, we can see that refinement take hold. You see 6 nodes. We see a hexagon around the middle of this boss that I did not refine. You can see that refinement actually does clean up that feature quite a bit. The 5 layers BLM is going to be created through the thickness of our parts, which we don't see here. We will break open the mesh to see that in just a moment here. The runner, you see that template, paste it onto the melt entrance and then extruded all the way through. It also matches to the part surface to give a one-to-one connection and passing over all the information exactly as we would expect. And the cooling channels also receive that hexahedral style with a 2-dimensional template extruded all the way along that line. The mold base is going to be tetrahedral, which, as it turns out, tetrahedral elements are very good at heat transfer. And it's also able to customize to all of the other components. You can even see on the surface of our mold base how the mold base elements are conformed to the cooling system that we've specified. Let's go ahead and hit final check once that mesh is created. What this will do is it's going to save our mesh file in both an editable format where we can go back and make any changes that are necessary. And it's also going to create what's called the MFE file, which you can see down here. It's going to be creating the MFE file, which is going to be used in the simulation itself. Once the final check is completed, it'll say the mesh is ready for analysis and you can press OK. This is going to pass us from the Mesh tab automatically back to the Home tab, where we can continue on with our simulation setup. But before we do that, I actually want to go through and slice open our mesh to see what the mesh actually looked like, so we don't just have to trust Moldex3D, that Moldex3D is creating exactly what we want. We want to actually see that. So I'm going to rotate down around so that I'm looking down on the top of my mold. I'm then going to go over to the Tool tab. So you can see a bunch of creating line functions, surfaces, a bunch of interactions, rotation functions, all those sorts of deals. But over towards the right, there's a chisel function. I'm going to use the chisel function. The way that this function works is I'm going to left click, drag a box. Any element contained within that box is going to be temporarily hidden. And it allows me to see the styles of mesh that are created for each different part of my geometry. Using the toolbar up at the top middle of your modeling window, right underneath the chisel function, there's this toolbar right here. The middlemost button on this toolbar, it looks like a little orthographic cube. That allows you to see the mesh. The first button allows you to see the mesh if you don't already see that. The last button in this toolbar allows you to see, turn off the transparency of the mold. And then finally, in order to get rid of this mold base object, you can either highlight it and highlight and then right click hide selected, or you can go to your model tree, which we haven't seen yet. You can go over to your model tree, which is just next to your project tree. And then you can find your mold base and you can hide the poly surface. Either way, it just allows you to see the solid mesh of your geometry a little bit more clearly. All right, so starting off with the part, we see that there's a 5 layers BLM created. We have 1, 2, 3, 4, 5 layers on the top, 5 layers on the bottom, and then the tetra layer to glue those two together. We see the hexahedral mesh created for the runner. Same thing for the cooling channels. And then the green mesh here is used to define the heat transfer between those different objects. Once again, the mold base is going to be tetrahedral in nature. And you'll actually see that the surface mesh size decreases in the actual heat transfer system between the cooling channels and the part. Moldex3D will do that automatically. And you'll actually see outside of that main heat transfer system, we see that the elements get quite large. The reason for that is just because there's not a whole lot of heat going out there, and Moldex3D recognizes that we can drastically reduce our element count by increasing the element size out towards the edges of the mold. This is actually why the dimensions of the mold don't matter a whole lot. If you have a larger mold base than necessary, you'll just have some larger elements out here. It's not going to increase your computation time significantly, and it's not even going to drastically increase the variance in the results. So for that reason, it's usually better to have a larger mold base than a smaller mold base. And that allows you to ensure that everything is contained within your mold while also giving you accurate results. All right, you can hit the chisel function. That will bring back the rest of your mold. Bring back the rest of the elements that were temporarily hidden previously. And then we can go back to the Home tab to continue on with our simulation setup. Now that we have hit the final check function, if you didn't do so, make sure in your mesh you have the final check as an actual check mark here. If it doesn't look like a check mark, make sure you execute that final check function. That will bring you back to the Home tab automatically. And then we're just going to pick up where we left off in this tab earlier. So if you remember, we started at the new run, we went over to import geometry, that brought us to the model tab. So we're just going to keep moving from left to right from the import geometry function. BC, we're not going to worry about too much. That allows us to set up like venting or heat transfer boundary conditions or stress boundary conditions. We do have a simplistic stress solver if you want to use that, but we're not going to worry about the BC in this training. If you do have any questions about any of the functions in the boundary conditions tab, I'd be happy to answer those later on. But to the right of the BC function is material. You'll actually see that this is the last available button at the current moment until the run. So this is the function that we need to use to move on to the rest of the simulation setup. We're going to hit material. And then this will bring up our material log where we can hit not specified. And under not specified, you'll see a couple of options. You'll see material wizard, which is going to be our database of materials. And then you have import, which allows you to create or import a material file from either a different project, or if, as I'll explain later, if we send you a material file, you'll be able to import it here. In addition, any materials that you've brought in previously will show up under the recently used section here. And if you have a user bank established, the user bank materials will show up in this dropdown as well for you to utilize at a more convenience. I'm going to hit Material Wizard, and that's going to open up our newly modernized Material Wizard interface. There's a couple of tabs over here on the left side. We have the project tab, which is where all of your material files in your project are going to be located. Currently, this should be blank because we don't have any material files. Your user bank is going to have a series of materials that you can use on a regular basis. Instead of having to search through the Moldex3D material database, you can add these to your user bank to find them a little bit easier later on. The third tab over here is the Moldex3D database, which currently holds about 8,500 material files. And is organized by polymer type, then by manufacturer, and then by grade name. We do have an awesome search function that allows you to search through this database. All right, so if I want to search for an ABS material, oops, I'm sorry. If I want to search for an ultramid material, let's say, that is PA66. And hit search, and it'll find all of the ultramid materials that we have in our database. All right, you can also use like very generic functions as well if you just want to search for an ABS material. Oops, ABS. You hit search, and it'll find all the ABS materials. So very, very easy to use. And if you have any questions about finding materials in the Moldex3D database, you can certainly ask us directly. This also allows you to search for some more advanced criteria as well, things like the MFI, density, filler content, recommended molding situations. And this newly modernized database also gives a good customization and good availability to query each of the components of the material files. I'll just go through those quickly. I'll just choose the first ABS material that shows up. All right, viscosity allows us to visualize how the viscosity changes with both shear rate and temperature. We can see that the viscosity decreases as the shear rate increases. And if we go from a low temperature to a high temperature, we can see that the viscosity decreases as well. This is more of a description of molecular orientation as well as shear characteristic. PVT allows us to describe how the volume of the part or the volume of the material specifically changes with temperature and pressure. So this is PVT, pressure, volume, temperature. And we can see from a temperature standpoint, if I just go from right to left, since the molding process is high temperature to low temperature, as I go through my cycle, as I go from a high temperature to a low temperature, we can see that the volume decreases, which is just a description of shrinkage. This is going to be the primary characterization that we use for material shrinkage in Moldex3D. We can also see from a pressure standpoint, as we go from a high pressure to a low pressure. Actually, I guess going from a low to high is a little bit more recognizable. So we go from 0 pressure to 200 MPa. We see that the volume decreases. This is a description of compressibility. Specific heat and thermal conductivity are just going to be your typical heat transfer characteristics. If the material was characterized by either Moldex3D or a different source, we will go to, sometimes you will see, sometimes you will see that the specific heat is a little bit different. Sometimes it'll have a peak, which we use for material consistency. If it is just a single value, it's not the end of the world. But if the material was characterized by Moldex3D or by some other reliable source, then you will see kind of a variation in the specific heat rather than just a single value. Viscoelasticity is a description of how the molecular chains interact with one another. All right, so the y-axis is modulus, x-axis is frequency, and the two curves here represent our G prime and G double prime, which aren't too important physically. It's more of a numerical attribution that's given. So viscoelasticity is allowing us to define how the modulus in the material is changing as the mold conditions change as well. Viscoelasticity is going to be applied while the material is still molten, but there is another property called structure VE that's going to take hold when the material freezes. This allows us to describe how the stress, the residual stress of our material, relaxes over time. So you can see that over time, our modulus changes, and also the temperature affects how this change is implemented as well. So structure VE, really an important property in addition to the viscoelasticity, is something that we are very heavily researching right now. Most materials you'll see will have very similar viscoelastic properties. And that's just because this is more of a micromechanics sort of property. So the molecular structure is more what's driving this than the blend. So from blend to blend, or even from manufacturer to manufacturer, some of these properties are going to be pretty similar. Until we start to test these materials more and more, we'll see that these properties are pretty similar to one another from a micromechanics standpoint. In the mechanical properties, you'll see things like your elastic modulus, Poisson's ratio, CLTE, as well as a little bit of other information. In the content tab, you'll see things like your filler content. If you have a fiber-filled material like this guy here, you can tell it's fiber-filled by this icon right here. If it is a fiber-filled material, you'll see the filler content, as well as things like the MVR and density. And towards the bottom, you see all of your recommended molding conditions, as well as your ejection temperature and freeze temperature. Source information tells us where this material came from, so whether it is a default material or if it's been tested by some other source. Here we go. So we have a Campus 5.0. Try to find one that's tested by Moldex. Literature, manufacturer can test them. And we're always going through and evaluating where these materials are coming from and what is the validity of those materials in Moldex3D. So you can trust that the material files that you're using are quality, are a high enough quality to trust the results as an output. So if there are any material files that are too low of quality, we will remove them from our database typically. All right, so I'm just going to use the first material file here in my project. To do so, I'm going to right click on that material and add to project. You can also add it to your user bank from here as well. All right, we see that the material has been successfully added. If I go back to my project tab, we see that the material file has been added. And you can close out of the material wizard. Once you close out of the material wizard, you'll see that the material file is automatically loaded into your project, into your run. And we can move on to the right of that, which is going to be our process. There's a couple of things that we can do for the process. You can either use a default process, which Moldex3D will just specify all of the information automatically for you based on the size of the geometry, your modeling layout, etc. Or you can create a new one, which you'll have the ability to edit. It's going to start from the Moldex3D default, but you do have the power to edit any of these values that you'd like. Now, there's two primary setting methods. I'm not going to go into too much detail about the specifics of what all is here. If you do have any questions about what specific parameters you can change, you can do so, or you can ask those in the chat section. We'll handle those later. But there's two primary setting modes for Moldex3D. There are CAE mode and machine mode 1. There's also a machine mode 2. We don't really use that one too often. We're usually focused on CAE mode and machine mode 1. CAE mode allows you to create more of like a predictive simulation. So if you're just trying to see how this part is going to behave in reality and a process hasn't been implemented, or this part is not yet in production, you can use CAE mode to get a generic process, and you can even use CAE mode to hone in on what process you should be using in your production cycle. Machine mode is going to be used more for a correlative method. So in CAE mode, you're going to be setting your parameterization a little bit more generically. In machine mode, you can even see that we specify what machine we're using. And in some cases, you can even apply a machine interface, which will allow you to interact with the machine's interface directly. You can even, from there, output a molding process sheet, which will just be a series of screenshots that you can take out to the mold floor and implement this directly on the molding machine. So very quite useful. But even if you don't want to apply the parameterization in the machine mode, you can still do so in the process wizard for Moldex3D. Again, I'm not going to go through the parameterization here too much. If you do have any specific questions, you can ask those later. I'm just going to hit next a bunch of times until we get to finish. And that will create the default process. That's pretty much the same thing as just pressing default here. And allows us to move on to eventually run the simulation. Moving on to the right of process is the analysis. Remember, we're just moving from left to right. We haven't abandoned that. We're moving from left to right across our interface. We want to make sure to do this methodically, especially when you're first starting out and using Moldex3D. It's very important to do this methodically so that you build a good best practice and so you don't skip over any steps. And this is one of the most important steps because if you just run a filling analysis and you walk away and you intended to run a warpage analysis, you're going to look at your results and say, oh, why is there only filling here? And it's because you didn't check this step. There's three analysis sequences that are typically used here. There's filling, we have filling and packing, and then we have the transient analysis. So filling just allows us to see the flow of plastic through our part. Filling and packing allows us to see the packing effect from our gate in addition to the filling of our part, and then transient analysis takes that a step further to take the part all the way to room temperature after the molding cycle and allows us to see how the final part shape looks like coming out of the mold. Note that the transient analysis sequence is only going to be available if you have a cooling system. If you don't, then it's going to allow you to run a fill pack warp, which is going to have an idealized cooling situation, which, like I mentioned earlier, is going to be way more idealized than what you would actually encounter in the real molding process. All right, so if you intend to run a warpage analysis, you want to make sure to change this to transient analysis. Everything in the computation menu is pretty good by default. We do have some specific parameters that you can change. We have a video up on our YouTube channel that goes over those. If you'd like to go check that out, it's Moldex3D North America. And then afterwards, you would just hit run, and that will launch the analysis. And then after the analysis is finished, you can come back and see the results. You don't have to launch the analysis right now. If you already did, that's perfectly fine. You can cancel the run and launch it after the training. You want to make sure that the resources on your computer are not completely consumed so that we can do the result interpretation smoothly. But if you want to run this analysis, I certainly implore you to do so after this training is completed. All right, we're going to take about a 10-minute break. And we'll come back and finish things off here with some result interpretation. How can we take the information that we've just calculated in Moldex3D and meaningfully interpret what we need to change or what needs to be iterated upon to improve the simulation results or to improve our molding condition going forward. All right, welcome back everyone, and we'll finish things out here with the post-processing result interpretation, how we can evaluate the results from our simulation. You can minimize your current Studio window, and we're going to open up a new instance of Studio. This does not consume an additional license. The license that's consumed by the first window can be passed to each of the additional windows. It does not consume an additional license. You can have as many Studio windows open at the same time as you'd like. And in this case, instead of hitting new, we're going to hit open. And that will allow us to find an existing project file. You can find the consumer project file. Instead of going into the CAD data folder like we did previously, we're going to scroll all the way down to the bottom and find the MRM file. You may also, for older projects, only encounter an M3J file. The M3J file you can choose down here at the bottom, or you can go to all supported files, and whatever file appears down here at the bottom is the one that you'll use. When you open up a pre-run simulation, you should see all of your input data over here on the left in your project tree, as well as your result information as well. So you can see that in addition to what we saw before, we have a new results section that has our filling, packing, cooling, and warpage results because we ran the transient analysis sequence. I'm going to go through each of these sequentially from top to bottom so that we can see a couple of the results and what tools I would use to interpret these specific results there. First things first, I'm going to go into the filling results, and I am going to turn off the mesh pattern as it does get in the way of the color contours a little bit. To turn off the mesh pattern, you can go to the toolbar at the top middle of your modeling window. The middlemost button that looks like an orthographic cube, you can go to the third option under that dropdown and go to show feature lines with shaded faces. That will turn off the mesh pattern and just show us the color contour. The first result that shows up in the filling stage of our analysis is the melt front time. Melt front time represents the amount of time it takes to get from our melt entrance to that particular location on the part. The contour itself doesn't really mean a whole lot, but what we're going to be looking at more is how the material flowed through our geometry. To do so, we're going to either hit the result button if we're following that sequence, going left to right across the toolbar. You can hit the result button and that will bring you to the result tab, or you can just click on the result tab manually. And we're going to be focused on the animation toolbar in here. You can press the play button to play an animation of the melt flowing through your geometry. And you can use the animation options here to change how the speed is. So if your animation is a little bit too quick, you can slow it down using the animation options. You can also use the little slider here to pull your animation back and forth if you want to see how the animation is through a specific feature. Like for example, if I want to see how the weld line here was created, I can zoom in there and then just kind of go back and forth on my animation. You can also adjust this percentage if you want to take screenshots at very specific percentage sections. You can even export this animation. If you click on the little video drop down here, you can export the melt front animation as a GIF file to put into a PowerPoint or whatever other format you'd like. The reason that we like to look at the melt front time results specifically is to evaluate what we call flow balance. Flow balance is the equivalency of having each end of fill out simultaneously. All right, what I'm typically going to do for flow balance is I'm going to push this percentage to 95%, just as a rule of thumb. And what I want to see is that all of my primary end of fill locations are unfilled at this moment. The further you can push this percentage and still have both end or all primary end of fill locations unfilled, the better your flow balance is and the more open your process window is going to be. There's a couple of reasons that we like to study flow balance. The first of which is going to be based on the pressure required to fill the part. I could avoid needing to look at flow balance if I just put my gate over on this side of my part, because the material has no choice but to flow in one direction until it hits the end of fill over here. But that means that our overall flow length is much longer. And as the material flows through our geometry, the resistance to flow is going to increase, and we're going to need more and more pressure to force that material through our geometry at a constant flow rate. So we like to study flow balance from a pressure perspective, but we also like to eliminate pressure spikes. What I'd like to do is go to the sprue pressure result. So I'm going to go to filling and then XY curve, sprue pressure. This sprue pressure curve is divided into three main sections. We have the feed system section, which is this initial rise in pressure over here. We have the pressure drop through the main cavity, which is the majority of this curve. And then we get to this maximum pressure value, after which is our transition to the packing stage. Now, any interruptions on this sprue pressure curve are typically not anomalies. Sometimes there are some small features that cause little bumps along the way, but blips like this in the middle here can be explained by looking at the melt front progression. What I'm going to do is I'm going to back up my animation to just before that little peak occurs. And we can try to identify what exactly is happening at this moment that might cause a momentary spike in pressure. I won't make you look too long. There is a corner, kind of like a secondary end fill that is completing its fill right over here. And what ends up happening is that as the flow develops, it has a choice in going one of three directions. It can either go towards the top left, bottom right, I'm sorry, top right, bottom right, and the left side. Once the material has completed filling the top right corner of our part, the momentum of the material that was going in that direction has to shift to either going towards the bottom right or towards the left side of our part. That momentum shift, which is kind of similar to like a wave rebounding off of a wall, that momentum shift will bounce back through the melt entrance and go either towards the left side or towards the bottom right side. And this is where these pressure spikes come from. Now, secondary end of fills like this usually result in a relatively low magnitude of pressure spike like what we see here. However, if this pressure spike occurs much later in our fill, closer to our VP switch, these pressure spikes will not only be higher in magnitude, but they can spike above the expected maximum pressure, which is going to be a large impulsive force on our machine, which can damage our machine and cause the amount of pressure requirement to be much higher than what we would expect. After this VP switch point, we're transitioning to the packing stage, and we're releasing the condition that we need to maintain a constant flow rate. I can add the flow rate curve to this XY plot by just right clicking on flow rate and add to XY plot. And we can see at this exact moment, that's when the flow rate goes from a constant value to a non-constant value. During this time, pressure spikes are not possible because we are no longer maintaining, or we never have to, we don't have to maintain that constant flow rate any longer. All right, so while 98%, or I'm sorry, while 95% is a good rule of thumb, I usually use the VP switch point, which is actually the maximum value here more times than not. I usually use the maximum value as the true balance point that I need to study. In this case, 94% instead of 95. Sometimes it'll be later, sometimes it'll be earlier. Moving on to another result that I like to take a look at is the temperature. The filling temperature allows us to see how the material adjusted its temperature throughout the fill. And what we're going to be looking at here more is the material that's in the core of our part or through the thickness of our part, not necessarily what's on the surface. The color distribution that we see is just the material that is in contact with the mold. We're more interested in what's inside of the frozen layer to see how the shear characteristics of the material changed along the flow path. There's a couple of tools that you can utilize here. The first of which is the clipping tool. In the inspection section of your result tab, you can go to the clipping tool. This will create a cross section on your part. And you can change the location of this plane by just left click dragging it. You can also change the orientation of this plane by changing what toggle you're using. So I'm going to use the XZ plane in this case. It just allows me to see how, first of all, how thick the boundary layer was, or how thick the frozen layer ended up being. And second of all, if I go from location to location, it allows me to see relatively how the temperature changed in my core. Now, generally speaking, this is a nice methodology, but there is a couple of other ways that we can do this same thing a little bit more effectively. I'm going to exit out of the clipping tool, and right below that is the slicing tool. The slicing tool effectively does the same thing, except instead of creating a cross section, it projects the result onto the plane specified. Like the clipping tool, I can change the plane location by left click dragging, and I can also change the toggle points. But the nice thing about the slicing tool is that we can place multiple slices along a particular axial direction. So for example, in the Y direction, which would be the XZ plane, I can place not only one plane, but let's say 10 planes. And I'll also, in the XY direction, which would be transverse to that, I'll also place 10 planes. This allows me to see a nice distribution of temperature throughout my core at a glance. So rather than having to kind of move that clipping plane back and forth, we can see all of these at once. And you can even uncheck this show plane to make things a little bit easier to view. Now, the primary use of this is to see how the temperature distribution changed throughout my geometry. And here, the core of my geometry looks to be pretty similar throughout my part. However, I think this is just because my scale is skewed due to my frozen layer being a significantly different temperature than my core layer. So I'm going to take out my frozen layer by changing my scale. This is kind of like what we did for the thickness distribution earlier. There's a couple of ways you can do this. You can just left click drag the minimum on your scale upwards, or you can double click on the minimum value and that will allow you to change it directly. I usually change this to somewhere around the freeze temperature just because that's where the, above that is the molten material and is what we're more interested in. In this case, I'll do something like 200. Once again, this takes out the frozen layer. So this distance here, this amount of material is the frozen layer. Anything inside of that is what the scale represents currently. And we can very graphically see that the end of fill is a significantly higher temperature than the gate region. Something even more interesting here, you can place probes on each of these locations. Down at the bottom right corner of your screen is a probe function. It looks like a little hand with a pointer. You can place a probe on a surface, and that allows you to identify what the temperatures are at those particular locations. That function just places the probes. You can go to display probe value, see what the values of those probes actually are. Right, and if you'd like to get rid of those probes, you can just go to your model tree. You can right click on the probes and get rid of them, or you can just highlight them and press the delete button on your keyboard. But either way, this result item allows you to see where the high temperature regions of your part actually are. And although this is a great way to visualize the temperature distribution, there is a better way even to identify where the hot regions of our part lie. All right, first thing, I'm going to close out of the slicing tool. I'm also going to reset my scale. To do so, I'm just going to hover over my scale, and there's a little toolbar that'll show up. There's going to be a reset display range that allows me to reset the extents of my original scale. All right, and just below the slicing tool is the isosurface tool. Isosurface allows us to break away all of the results in our display except for one singular value. And that's shown up at the top left corner. You can see currently the value that's shown is about 180 degrees Celsius. So only the elements that are at exactly 180 degrees Celsius are the ones that are showing. And if I move the slider towards the right or towards the hotter end of my scale, I'm going to see a bunch of the material start to go away, and only the hottest material will remain, really showing a good distribution or a good indication of where the hottest material lies in my geometry. And we can see from this, kind of like what we saw from the slicing matrix, you can see that the hottest material is in fact the end of fill. And the reason we like to look at the temperature distribution and where the hottest material lies is that we can identify which of the two effects dominated. We have the cooling effect, where the energy from our melt is being released into our mold. And we have the friction or the shear effect, where the material moving through the core of our geometry is rubbing up against the frozen layer. That friction is converting the energy into heat, and that is going to increase the temperature of our melt. The cooling effect is going to gradually decrease the temperature of our melt. So which of those effects dominates is going to dictate where the hottest material at the end of our filling is going to be. And it's very possible for either situation to occur depending on the speed of our material through our part. In this case, we see that the temperature is higher at the end of fill, indicating that the shear effect dominated the cooling effect. And that's just indicated by the fact that the temperature is higher at the end of fill than it is at our heating source. That means that the temperature gradually increased over the length of fill. If the opposite were true, if the cooling effect dominated, then we would see the hottest material is at the gate location. In an ideal world, you're actually able to balance these two effects, and you'll get a nice uniform core temperature You won't get a skewed temperature distribution either towards the end of fill or towards the gate location. Everything will be nice and uniform, which if everything is at a nice uniform temperature, that means it's going to shrink at a uniform rate, which means that you're going to reduce the potential for warpage from a core temperature perspective. There can still be warpage based on the surface temperature, based on your cooling system, and so on. But from the core of your geometry, the shrinkage will be more uniform and will give you a less probability or a less magnitude of warpage. Moving into the packing results, let me get out of the isosurface tool. Moving into the packing results, one of the first things that I always look at is the packing pressure. Oops, packing pressure. The reason I look at packing pressure is so that I can see what the distribution of the packing effect looks like at that particular moment. We can see in this case that the pressure is quite isolated around the gate. And the thing to keep in mind here is that the pressure can only distribute through molten material. So if there's any frozen material, that's going to inhibit the ability of this pressure to distribute through the rest of my geometry. Typically, I like to put this result side by side with the result that we call the molten core so that I can see where the molten material actually is in my geometry at this time instant. First things first, I'm going to go to my compare tool in the result tab all the way towards the right. You'll see the compare tool, which will allow you to have two windows. I'm going to keep one as my packing pressure. I'm going to make the other one my active window by left clicking on it. You can see that it has the blue name instead of the gray. It makes it my active window and gives me the ability to change the result. I'm going to change the second window here to molten core. And to make sure that I'm kind of rotating around these and zooming them in at the same time, I'm going to turn on what we call sync rotate. All right, this just makes it so that I rotate both windows at the same time, zoom in, zoom out. Just makes it a little bit easier from an interface perspective. That's the sync rotate. All right, and we can see from this comparison that at this time instant, the pressure is quite localized around the gate because the gate is isolated in molten material from the rest of the part. This blue material here represents a temperature greater than the freeze temperature, which in this case is 150 degrees Celsius. So any material over 150 is what shows here. Everything that's transparent is frozen off. So we can see that the material is isolated around the gate and it cannot distribute out to the rest of the part, even though the end of fill is still molten. There's no way for the material to get there because there's frozen material in between. And this will almost always happen with shear dominated flow. Obviously, I have hot material at my end of fill. There's going to always be material coming in behind that through the melt entrance. So molten material is always going to be coming in through the melt entrance, but there's nothing heating up the intermediate region. And so that's going to isolate the gate off from the end of fill. And you end up getting this very localized distribution of pressure as a result. Now you can use this to kind of figure out what your ideal packing time it should be. You know, if I'm only pressurizing the material around my gate, maybe that's unpreferable. And so maybe I want to go back to a previous time step or a different time instant to figure out what my ideal packing time should be. To do so, you can right click on any result. And you can select what time step you'd like to use. So in this case, if I go back to the 9.98 seconds, we can see that the material is much more, more of the material is molten which means that if I go to the same time instant in the packing pressure, oops, molten core, same time instant over here, we can see that that pressure is much more distributed. However, what this means is that the material hasn't frozen yet, so we're going to need more cooling time in order to get this material to an ejectable state. So it's always a kind of a trade-off as far as how you want to handle your processing, how long you want to be applying the pressure versus how long you want the part to just be sitting in the mold, cooling off and getting ready to eject. All right, but this is something that simulation can evaluate, and it's something that we typically do take a look at very intensely. Moving into the cooling results section, I'm going to get out of the compare tool for the time being. Moving into the cooling results section, there's a few things that we can do here. The first thing is that we can look at where the hot spots are on the surface of our part. This might allow us to evaluate where we need to improve the efficiency of our cooling system. Now, the temperature in the core of our geometry is still going to be quite a bit hotter than the surface. What we're more interested in here, whereas in the filling stage, we looked at the core temperature, in the cooling stage, typically we're going to be looking at the surface temperature to see how the cooling channel layout affected the temperature distribution across the surface of our part. And so I'm going to reduce the maximum on my scale to remove some of that material in the middle of my part and just show the temperature distribution on the surface instead. If you get something like this, it just means that it's outside the extent of our current range. You might just need to extend that a little bit higher. All right, but this allows us to see where the highest temperature material is. And if we turn on our cooling channels, you can go to your model tree and turn on your cooling channels. This allows you to kind of evaluate where your cooling channels could be improved. So we see that there's a big hot spot on this part in the bottom channel here. Looks like there's a big, relatively high temperature region right in this corner. And so maybe I need to make this a little bit more conformal along this channel. Maybe I can bend this cooling channel down so that it gets a little bit closer into this corner. I think one of the biggest misnomers about cooling design is that the cooling channels act as a magnet for heat transfer. And that's not really the case. The cooling channels will remove the heat locally from where the cooling channel is, but it will not attract heat out of localized regions like this. So although getting the cooling channel close removes some of the heat, it does not remove enough of the heat to prevent a hot spot from being there. All right, so maybe I need like a baffle or conformal insert, something like that will allow me to remove that heat a little bit more efficiently. But beyond looking at the temperature of the part, I can actually look at the temperature of the mold. Because we use solid mesh for every object in Moldex3D, I can actually look at the results in my mold base as well. All right, so if I turn on my mold, I can use the clipping tool like we used earlier. Use that XZ plane. You can actually see how the temperature is distributed at different parts of the mold. Now, again, this is going to be a little bit skewed by the part geometry, so you can either turn off the part, that'll allow you to get a better scale, or you can kind of like what we did for the part temperature, you just take the scale down. That will allow you to see that temperature distribution a little bit better. All right, once again, these are outside of the range of my scale, so I'm gonna maybe increase that a little bit more. There we go. Now, interestingly enough, you can create a time series animation. So you can actually play an animation of this over the molding cycle to get an idea of how that temperature was changing. What was the thermal cycling on either the mold itself or on an insert, whatever it would be. You can do that by going back to the Result tab. You can hit the video dropdown and hit time series. That will create a time series animation in either AVI, GIF, or MP4 format. This is very useful for cooling channel design and is a good way to communicate either the how well the mold is designed or where there are deficiencies. Both sides of the coin can both be displayed here. All right, I'm going to turn off my mold base. I'm going to turn off my cooling channels. And another result that I like to look at here is the time to reach ejection temperature. Time to reach ejection temperature allows us to evaluate our cycle time. Because the cooling time is the longest part of our cycle, usually this is where we can afford to save the most time on. Now the scale here is in time. The scale is in seconds. So this is just indicating how long it takes for each element to get down to what we call the ejection temperature. If I go to my information tree, it looks like a circle with the letter I. We can see in the material section, we see our freeze temperature, which is 150 degrees Celsius in this case. But then we have our ejection temperature, which is 120 degrees Celsius, so 30 degrees below the freeze temperature. So what this result is telling us is not how long it took for the material to freeze, but how long it took for the material to get 30 degrees below the freeze temperature in this case. This ejection temperature is something that you can change in the process file if you want to eject at a little bit of a hotter temperature or a cooler temperature. You can apply that in the process and you'll be able to evaluate that here. Now, based on the scale, you might say, oh, okay, we need 60 seconds in order to cool down this part. No, that is not the case. 60 seconds represents how long it takes for the hottest element in our part to get down to the ejection temperature. It's not necessarily representative of the entire part geometry. To evaluate this a little bit further, we're going to use that ISO surface tool that we used in the temperature distribution earlier. We should be towards the top of our scale already, because that's where we were in the temperature. It just takes that same percentage of the scale. And we can actually see that the top of the scale really just represents the material in our gate. All right, so this little ball of material, if we go down in our time, which means that the amount of time that we need to get our part down to the ejection temperature is decreasing as we scroll to the left. I'm going to keep going until some feature on my part starts to show up. So what this is saying is that in order to get my entire part down to the ejection temperature, I would need about 44 seconds. However, we don't need the entire part to get down to the ejection temperature. We can have some localized features like these bosses, like these thicker features on the side of our geometry. We can keep those above the ejection temperature and let them cool down outside of the mold. So I can take this down a little bit and we'll start to see some of those thicker features show up. I'm going to keep going until a major feature or a major surface on my geometry begins to appear. Just before that point is where I would say my cooling time should be. So maybe in this case, somewhere in the realm of 15 to 16 seconds. But even from there, if I'm looking at the simulation results, I will know where I can strategically place my ejector pins so that I don't have to interact with these hotter surfaces. In this case, we saw from the thickness distribution that this surface is about 0.5 millimeter thicker than the rest of the part. If that's the case, then we can just avoid putting ejector pins on near this surface. And that in that case, this surface almost is similar to these bosses. We can just let it cool outside of the mold. And as a result, we can save a little bit on our cycle time. All right, so maybe I could go down to something like 10 seconds instead of 17 seconds. And this is where simulation can really benefit you, allowing you to see where the hotspots are, how long it takes for each of these features to cool down, and ultimately where you can save time and money in your production cycle. To wrap things up, we're going to go into the warpage results. Before I dive too much into the warpage results, one of the things I like to emphasize is that everything that you see in the warpage comes from the filling, packing, and cooling. More times than not, I see users will go in, look at the warpage, they'll see the color distribution, they'll see where the part is warping, and then they'll go into the filling, packing, and cooling to see where that warpage is coming from, which is really quite backwards from what you should be doing. If you look at the warpage first, you're going to be biased and you're just going to be going on a wild goose chase to find out where that warpage might have come from. Instead, you should be going through the filling, packing, and cooling to get a premonition of what that the warpage results should look like. And if those warpage results are not what you expect, now you have a more educated result interpretation methodology to go back and figure out why that might be the case. All right, so it's very important to be looking at the filling, packing, and cooling before going into the warpage. This will save you a lot of time and it will save you a lot of frustration because it's going to answer more questions than it creates, whereas going to the warpage results first creates more questions than it answers. That being said, the first result that shows up in warpage is total displacement. Total displacement represents how far each node moved from its original location. I typically won't look at the results like this. I will use the deformation function, which will deform my part and actually show me visually how this part is warping. So in the result tab towards the middle in the warp section, I'm going to go to deformation. And that will just visually show me how the part is moving. All right, so this 0.972 millimeters represents the distance from our original mesh, which is the wireframe, to our new colored deformed mesh. And very importantly, this total displacement does not represent a direction. It just represents a magnitude. So just looking at the total displacement by itself is not necessarily indicative of what direction that part is moving. So it is very important to be looking at deformation in order to see how that part is ultimately visually changing. Sometimes for parts, the magnitude of displacement is quite low with respect to the size of the part, and so you might need to scale the displacement a little bit. I'll usually use a 10 times scale factor. Kind of depends on the magnitude of the warpage, honestly, or the magnitude of the shrinkage. And it's very important to note here that there are two different effects that are included in this result. We have not only the warpage of the part, but also the linear shrinkage of the material. All right, so linear shrinkage as well as the differential shrinkage, which is just another name that we give to warpage. Both of those effects are included into this result. And so with that in mind, let's evaluate both of our high displacement regions. We have one displacement region on this end of fill and one over here. All right, so this guy, if I rotate around to the side view, we can see that there's a good amount of movement in the Y direction. There is a little bit of movement in the X direction, which would be vertically as I have it shown here. If I rotate 90 degrees, you see that there's not a lot of movement left to right or in the Z axis. So most of the movement being in the Y axis here tells me that this material is pretty much just linearly shrinking, which if you think about it makes quite a bit of sense. Because we saw that this material at the end of fill was the hottest material in our part, well, also the other end of fill, but some of the hottest material in our part. And also because of that shear dominated flow effect, we weren't able to pack out this region very well. So that means that this material is going to shrink quite a lot. And there is going to be some sort of culmination effect as well. As we get from our melt entrance to the end of fill, each element is going to shrink a little bit, and that's going to culminate over the length of fill and give us our final displacement like this. If we go to the other side though, I don't know how obvious it is, but we can see that there is a little bit of warpage that's happening on this feature. You can see that it's kind of bowing inwards. And that's probably because the material around this surface right here, remember down in this channel, there was a hot spot. Well, that hot spot is causing that material to shrink at a much higher rate than the material on the other side of the part. And that's going to pull all of the surfaces inwards. Unfortunately, this surface is the only one that has a degree of freedom to deflect like that. All the rest of the surfaces are kind of mechanically bound. We see a similar effect maybe over in here as well. All right, so linear shrinkage and differential shrinkage are both included into this result, and we need a way to separate the two. That's where the mold compensation comes into play. Mold compensation allows us to input the material shrinkage value, and then that's going to remove effectively the linear shrinkage from our part, just leaving the warpage or the differential shrinkage. All right, so I'll let you guys know that this PCABS material has a 5/1000th of an inch per inch shrinkage, or 0.5%. All right, so I'm going to input 0.5 because we're using isotropic compensation. All three directions are going to have the 0.5 compensation applied. If you want to apply different compensation values, you can use anisotropic. But what we see when we apply the material shrinkage value is that the left side of our part flips from the red side of our scale all the way to the opposite side, kind of a lighter blue color, indicating that almost all of that displacement that we saw was because of was because of linear shrinkage. However, this side of our part remains red, indicating that even though we have compensated for the linear shrinkage, there is still some differential shrinkage left over. You can see that on this corner as well. Now, interestingly enough, you can export this deformed model. So if you want to compare it to the real molded geometry, if you have a scan of the real molded geometry, you can use this as a comparison for the accuracy of the simulation. To do that, you're going to go into Export Deformed Model, and you would apply a scale factor of 1. If you ran the simulation on the mold geometry, the output from the simulation would be your final molded geometry, or what we would predict as the final molded geometry. However, you can actually change the scale in here to a -1, which would be a reverse deformed model, or what you could consider as a windage model. So if you wanted to, you could export the windage model. In the current state, you can only export STL files, but something to be very excited for in 2024, next year, we are going to have a conversion to step file. So you'll be able to export a step file directly from this function. And from that step file, you can import that step file directly into your mold geometry and design around it. This is going to create an awesome closed loop simulation. That is a huge step in the right direction for automated simulation and automated design. There's a couple of other tools I want to go over before we wrap up here. I'm going to exit out of deformation. The first one is the distance tool. The distance tool allows us to, well, measure the distance between 2 points. All right, cool. But if I'm in the total displacement results, I can hit save and close, and that'll give me not only the distance between those 2 points, but also the deformed distance between those 2 points, as well as the linear shrinkage. So if I have a dimension that I have to hit, I could take the distance, let's say between these 2 corners here, 1 and 2, save and close. And then I can see if this deformed value is within my given tolerance. All right, very awesome tool, something that you can use for dimensional validation. And these distance measurements show up under your model tree. I'm going to delete the ones that I just created, but you can turn them off to get rid of them as well. All right, it also creates a bunch of probes that I'm gonna remove from my results as well. The flatness tool allows us to take a flat surface and measure it against a kind of like an average flatness plane. To create the flatness selection, I'm just going to select one element on the surface that I'm querying. That will propagate that selection to the rest of that surface. When I hit save and close, it's going to isolate those elements from the rest of my geometry. It's going to create an average flatness plane. And the distribution that we see across these elements represents the deviation from that flatness plane, either up or down. So anything in the positive direction would be above this plane, anything in the negative direction would be below this plane. The flatness rating that we get here is just the difference between the maximum and the minimum. So theoretically, as we get a lower and lower deviation, the difference between our maximum and minimum decreases, and eventually we approach 0. A flatness of 0 would mean that the surface is, in fact, completely flat. Once again, this flatness reading shows up in your model tree, and you can delete that appropriately. The roundness tool allows you to measure the roundness of a particular feature. So if I go down to one of these bosses, I can hit roundness and just select one of the mesh edges on that feature. It'll propagate once again to the rest of the circumference. I hit save and close, and that gives me a roundness rating, which is the difference between the deformed maximum radius and the deformed minimum radius. Kind of like the flatness plane, as we get to a perfectly round feature, the maximum minimum radius approach equivalency, and so the roundness rating would approach 0. Measuring face is actually very interesting, and especially in the context of warpage. What it allows you to do is isolate a particular group of elements for a result. And this doesn't only apply to warpage. This could be done for temperature, pressure, fiber orientation, whatever you would want to do. I'm going to select an element on the surface, just like I have for the previous tools. I can use a control box select to deselect the elements that I don't want. All right, so maybe I just want the elements on this side of the feature. And then I also get to select what elements of that, or I'm sorry, what statistical information I want to extract from that surface. So let's say I want to see what my average displacement is across this surface. I'll hit save and close. That's going to isolate that surface, kind of like what the flatness plane did. And you'll see that it'll only show the scale for these elements specifically. And we also get the average displacement across this group of elements as well. This is extremely useful, not only for warpage, but a lot of the results in Moldex3D. If you want to just break down the statistical information for a group of elements, is a great way to do it. Radius of curvature is going to be kind of similar to flatness, but for a curved surface instead. If I have a curved surface on my geometry, I can select one element and propagate just like the rest. What this is going to do is if the radius was nice and uniform, which in this case it is not, it'll give me the average radius of this surface, and it'll give me the deviation from that radius as a distribution of color. All right, so we see that the radius is the average radius is kind of the green color because the maximum and minimum on my scale are positive and negative. So the 0 would be our average radius. And theoretically, if we have a perfectly round or perfectly consistent radius, then the deviation between the maximum and minimum would approach 0, just like the flatness. One last thing that I like to show off is the results status saving. And this is something that was introduced in 2022. So let's say I go to an isosurface and actually let's go to the filling, temperature, isosurface. And let's say I want to see where the hot material is located. That's a lot of clicks to get to that point, right? You have to go into the isosurface function and you have to adjust your isosurface slider accordingly. What I can do is in the result tab, I can use the new result. This will create a new result item under the customize group section of my results. And so there's a new customized group here. And so instead of just looking at the, instead of, if I exit out of my isosurface, instead of having to go back to that point, I can just go into my saved result and it'll go to that exact result condition. You can also save over a current results. Like for example, if I had a melt front time and I wanted to, I don't know, maybe I want to show the ISO contour, for example. Oops. I can hit save result status. That will create a note under the melt front time result. And so even though I close out of that ISO contour, when I come back to the melt front time, we see that it's back in the ISO contour view. So it just kind of saves how the result is showing and allows you to minimize the number of clicks that are required to get a result back to the exact configuration that you had it. And that's going to wrap things up for the Moldex3D standard training here. We thank everybody for joining. And we hope to see you in one of the future Moldex3D events, online tutorial sessions, or Molding Innovation Day locations. Thanks, everyone. All right, if anybody has any questions, you can send those into the chat, and I will be happy to answer those. So there's a couple of unanswered questions here. Would sync be visualized in the warpage analysis? The answer is yes. If you were to deform your, or if you were to use the deformation tool, you'll be able to see the sync in your warpage. There has been reportedly some issues when exporting the deformed model that the sync does not appear as pronounced as it does when you deform the model in Moldex3D. So that's something to think about. But in the results themselves, you should be able to see the sync in the warpage results. I see you found where the part went to the vacuum cleaner. Yep, nice. All right, if there's no additional questions, then we'll end it here. Thanks, everyone. And if you have any questions, you can reach out to us. I'll be happy to answer any questions that you have in the